Welcome to your geometry lesson for week 6, and we're going to take a look at radii, chords, and tangents. So you already have completed the Desmos activity and discovered that the relationship between the radius and the tangent line at a certain point is a perpendicular relationship at the point of tangency. So we know that our tangent theorem states if a line is tangent to a circle, which this gray line is tangent to our circle A, then the line is perpendicular, meaning creating right angles, to the radius of the circle drawn at the point of tangency. So this relationship exists for every point of tangency on the circle. Now let's take a look at the relationship between the radius and a chord. So I have my radius AB and my chord DG. Now I can move that radius AB so that it is perpendicular to DG. Here, if it is perpendicular, meaning that it creates a right angle, then we know that it cuts the chord directly in half. Each side, DH and HG, are equal. They both equal 2.64 units. Our radius and chord theorem states that a radius that is perpendicular to a chord of a circle bisects that chord. So a radius AB that is perpendicular to a chord, meaning it creates right angles to this chord here, then it bisects this side and this side to be equal. So we can take a look at the proof to show why this works. So if I know that AC, this chord, is perpendicular to XB, that's given, I'm trying to prove that AD, this line here, is congruent to DC. I know that angle XDC and XDA are right angles because that's the definition of perpendicular. Then I know that triangle ADX on this side here and CDX are right triangles. I know that because they both have right angles. So that's the definition of a right triangle. AX is congruent to CX because these are both radii. So obviously they are going to have the same length. DX congruent to DX, reflexive property. And you thought we were never going to use this again. Triangle ADX is then congruent to CDX by hypotenuse leg. The hypotenuses are congruent and they have a leg that is congruent. Therefore, AD has to be congruent to DC because of CPCTC. Congruent parts of congruent triangles are congruent. We can take a look at the converse of the radius and chord theorem, and we know that a radius that bisects a chord of a circle is perpendicular to that chord. So now I'm going to work backwards. If I know that AD is congruent to DC, and I want to prove that XB is perpendicular to AC, I'm just going to work backwards. And you can take a look at that proof here. Again, a radius that bisects a chord of a circle is perpendicular to the chord. So let's take a look at an example. AB is a line that is tangent to circle C at point B. So point B is my point of tangency. If BC is 6 and AC is 10, this is a right triangle. I know this is a right triangle because my radius here meets the tangent line at the point of tangency, creating the right angle. So what I can use is the Pythagorean theorem. A squared plus b squared equals c squared, so I can solve for b. Let's take a look at how that works out. 6 squared plus b squared equals 10 squared. 36 plus b squared equals 100. B squared equals 64 because I've subtracted 36 from each side. And the square root of 64 is 8. So therefore, b equals 8. Let's take a look at another example. I know that AD is the radius of circle A, and AD, that same radius, is perpendicular to the chord BC. So those are my gray lines here. If I know that BC, this whole chord, is 5 and AC is 3, I need to find the area of ADC. I just want to find the area of this side. So I'm going to need to find some missing pieces of my triangles. So first I know that the area formula is 1/2 base times height, or base times height divided by 2. So I have my distance of AD, which is 3. I know that A equals 1/2 times 3 times 2.5. Therefore, A equals 3.75 units. Again, we take a look at our example just to reiterate that our radius bisecting a chord creates the 90-degree angle. If a line is tangent to a circle, then the line is perpendicular to the radius of the circle drawn at the point of tangency. A radius that is perpendicular to a chord of a circle bisects the chord. And that's all we have.